Okay, hi guys. So in this lecture, we'll be discussing on ionization energy. Okay, so let's get started. Ionization energy. Okay, so let's say we have a reaction in which H plus G is converting into H plus G and electron. Okay, so this was in ground state. The electron in Hg was in ground state, and the conditions are it was isolated gas atom. Okay, so when Xg, for a general reaction we are talking, so in this case the ionization of Hg took place. Okay, so this was just a simple example. So now for a general example, so when the electron is in valence shell, maximum energy of electron would be there. Okay, and as the electron gets closer to the nucleus, the energy lowers and lowers itself. Okay, so I'm just talking in terms of mathematical positive and negative signs, but if you take the mod of it, obviously the energy of the electron closest to the nucleus would be the highest. But for mathematical term, the electron's energy nearest to the nucleus would be lowest. Okay, so this would be in some negative value. Okay, but obviously the energy would be in will be having a negative charge only, as we saw in the case of total energy already. That total energy was calculated with minus 13.6 and some relation of Z and N. Okay, so but if you take the mod value, the energy nearest to the nucleus would be the highest. We are talking about this in relative or mathematical terms. Okay, so energy required to move an electron, or rather to remove an electron from isolated atom present in gaseous state, is called ionization energy. So in this case we can define ionization energy is as energy required to remove an electron from isolated atom present in gaseous state. Okay, so it is always, ionization energy is always positive. Okay, as the work has to be done on the system to remove the electron. Okay, as work has to be done to remove an electron. Okay, next, so let's suppose the energy of valence electron in Hg would be, so Z here is 1. Okay, and N here is also 1. As the valence electron is, we are considering N equals to 1 or K shell. Okay, so energy would be minus 13.6 Z square upon N square, which would be 1. So it would be to minus 13.6 electron volt. So energy required to ionize H into H plus would be 13.6 electron volt. This much energy needed to be provided to convert this into, or rather H atom into H plus ion. So if we, this is electron volt per atom. Okay, so let's convert it into joule per atom. So electron volt would be, charge on electron volt is 1.6 into 10 to the power minus 19 coulomb, and then for coulomb to joule we would rather use 6 into 10 to the power 23 joule per. So now this electron volt is converted into joule, and per atom would always be there. Okay, so it would be 13.6 into 1.6 into 10 to the power 4 joule per mole. It gets converted into 1.3 into 10 to the power 6 joule per, not mole, per atom. Okay, so this much energy is required. Okay, so now let's move on to discuss the limitations of Bohr model. So first is, it is applicable only for electronic species, that is H atom and H like atom. Okay, so it is applicable only for unielectronic species, so H atom or H like atom. Okay, next is, he could not explain line spectrum of helium atom and others. Helium atom and others. So please remember that though we say that in Rydberg's equation also, that 1 upon lambda is rz square upon n1 minus n1 square minus 1 upon n2 square, we take z. So why is it not applicable for other atoms apart from hydrogen atom? They are applicable, but only for the ionized part of that particular atom. So let's say we saw an example wherein we use H plus. Okay, so as to indicate that there is only one atom in this species. Okay, helium originally has 2 electrons, but we have converted into He plus, then it only has 1 electron, just like hydrogen atom which has 1 electron. Now the Z for this He plus still remains 2, unlike H atom wherein Z was 1. Okay, so we mean that it is only applicable for unielectronic species which have only 1 electron, just like hydrogen atom or hydrogen like atom. Okay, so Z could be different, but the number of electron in that atom should be 1. Okay, so third, that he cannot explain fine line spectrum of hydrogen atom. Explain fine line spectrum of hydrogen atom, which is nothing but further splitting of lines and also was unable to explain splitting of light in presence of magnetic field. Splitting of light in presence of magnetic field. Okay, so, or in other terms, he could not explain the Zeeman effect and Stark effect. So in presence of magnetic field, we have Zeeman effect, and in presence of electric field, we have what is called as Stark effect. Okay, and next is Bohr model is not applicable or is not according to de Broglie's concept and Heisenberg uncertainty principle. Okay, Bohr's model is not according to de Broglie's concept and Heisenberg uncertainty principle. Okay, then he could not explain why angular momentum of electron is quantized. Why angular momentum of electron is quantized. Next, he could not explain 3D model of atom. Could not explain 3D model of atom. Okay, so with this we come to the end of this lecture. In the next lecture we'll be discussing on de Broglie's concept.